Okay, I kind of put some mood lighting up here to kind of, because they said the glare was off the board. So if it looks dark in here, that's why. Okay, so a couple of housekeeping things. Some of you have sent me in like that scanned cell phone letter, okay? When you send stuff to me with that scanner app, send it from your school address, because that's what I have stored in like my contact list. So if you send it from your personal email, then on the cell phone letter it doesn't make any difference. But when I get stuff from other assignments and things like that, when I go to send it back, I have to send it back to your school email account. So that's where all that transition is going to be happening, is through that school email account. So if you haven't scanned in that letter, most of you have, some of you haven't, just make sure I get that cell phone letter back. So here's what, and again, this week is kind of screwed up for any number of reasons. But yesterday I posted a lecture on dimensional analysis. You all should have gotten that in an email with a link to YouTube. Did that? Okay. So what I just handed out is the assignment that goes with that, which is going to be due on Monday. Okay? So you're going to scan that, send that back. There'll be 2 pages. Take a picture of one side, flip it over, move those up. If you have, and don't think it has to be handed in like before class starts on Monday. My plan on Monday is to go over that assignment, that dimensional analysis assignment, and give you some time to work on it. So if you have questions and things like that, just wait, and then we'll go over that in class. The lab that you're going to do today is also going to be due on Monday. So for like your time log for tomorrow when you're all remote learning, that's what I've got on that calendar that I printed out. So theoretically, I think I put the lecture to be like 50 minutes and the homework to be like 40. The lecture turned out to be like 40 minutes. It's okay. Go ahead and put it down to 15 minutes. I kind of estimated what I thought it was going to take to get through that. So that's what you're going to, that's when you start to fill out that time log for tomorrow. You've got the lecture at, I don't remember, I think it was 50 and the homework at 40. Okay? Unless some of you said you don't get done with that assignment pretty soon. Some of you might take more than 40 minutes. I was just trying to guess on that amount of time. Okay. So, then there's also the lecture on the MKS. If you haven't watched that, let me just go over in seconds, kind of watch that. So, and then today we're going to do this lab. Tomorrow, my other class, the other half, is going to be doing this lab as well. So tomorrow you don't have to worry about zooming in, because they're going to be doing the exact same thing you guys are. Now, starting next week, okay, when I have you guys on Monday, then on Tuesday, we're going to be doing something completely different. So then, like next week, and we'll talk about this, because I'll remind you, because I might forget to. So on Tuesday, that's when you all need to plan on actually zooming in, okay? Because we're going to be doing something completely different on Tuesday in terms of like the lecture and the homework and things like that. So I just wanted to plant that seed, so we got that covered. Okay, make sure your cell phones are up there. If you haven't put your cell phone up there, chuck that up there into the holder if you would, please. Okay. Okay, so the lab today is kind of going to get you back into the flow of graphing and some unit conversions and slopes and things like that. So what we're going to look at today in the lab is the relationship between how much force I apply to a spring and how far it stretches. Okay, so that's going to be the big idea. So we're going to have 2 variables. We're going to have force and we're going to have elongation on how far it stretches. So let's go back to the beginning. So I'm guessing probably since maybe, I don't know, maybe 6th, 7th grade science classes have taught you the difference between independent and dependent variable. Okay, so what is the difference between an independent and dependent variable? Yes?
The simplest way would be input, output. Independent is what you can change. Dependent is what happens because of what you're independent to do.
Okay. So here's the biggest thing. Your independent variable is what you control. Okay? That's your independent variable. So in this situation, we're going to be dealing with how much force that we apply to the spring. That's our independent variable. Now this definition is a little bit cyclical. but your dependent variable is dependent upon changes in your independent variable. So my elongation is dependent upon the change to my independent variable. Okay, so that's why I said it's kind of a weird cyclical definition, but it really kind of fits. Okay, so when you graph these, and this is all on the back of the lecture notes, it says, like, in the beginning, physics without form. I've got all of these definitions on the back of that sheet. If you want to write it down, great. You don't have to. That's why I gave you the lecture notes. Now, I will tell you a word of caution, okay, is that I don't care what you all write down. Some people write down everything. Some people just sit there and kind of soak it in, okay? That's up to you. It's whatever your learning style is that fits for you. But there's the caveat. When we get into working these big complex problems eventually, okay, when we eventually get into that, and if you sit there and don't write down anything, okay, like you write down nothing on these big complex problems that I write, and you come up to me and go, hey, you know, Mr. Burkamp, I don't understand number 5. And I'm going to ask you, like, what did you write down on the problem that I worked? And if you say, I really didn't write down anything, maybe the first couple of times I'm willing to let that slide, but if you get into a consistent pattern of not writing down anything, and then basically coming up and asking me to reteach it to you again, my patience at that point will begin to wear thin, okay? Now, I'm not going to grade your notebooks. I have 1,000 things to worry about. Grading your notebooks is not on the list. Okay, you all are big people. You know the learning style that works for you. If you want to write stuff down, great. I always did, because I always found that I remembered it and I understood it better if I summarized it and I wrote stuff down. If you do that, that's up to you, okay? You all are big people. That's a decision that you all need to make. So, a couple of things about the independent variable. That's the one that we graph on our x-axis. And that's what we're going to graph on our y-axis. So, Ryan, what kind of car do you drive?
A Nissan Altima.
Nissan Altima. Okay, so here's what we're going to do. We're going to look at a simple example. So we're going to have Ryan, we're going to go out into the parking lot, and here's the Nissan Altima Carrot car. Okay, that's what your car looks like? Yes, it does. Thank you. Okay. And we're going to look at two different things. We're going to look at how fast Ryan is going, his velocity, and how far it takes for him to stop. Okay, so we're going to have two variables, velocity and stopping distance. So he's going to get up to about 10 meters per second, and he's going to cross the line, and then he's going to hit the brakes, and then we're going to see how far it's going to take to stop. So he might be going like 10 meters per second. Now, to give you some perspective on meters per second, okay? 10 meters per second, that's like a world-class sprint. Okay, if you can run 10 meters per second, you are going to be in the Olympics. Okay, that's a world-class sprint. Most people at a full speed will run between 6 and 8 meters per second. So 10 meters per second, that isn't like, you know, oh, you're going to win the Indianapolis 500 with this. But, you're moving. So he's going to hit the brakes, and it might take him 3 meters to come to a stop. Okay? And then we're going to get him up to like 20 meters per second. Woo! I want to see how far it's going to take to stop. And then we're just going to get these data points. Okay? How fast he's going and how far it takes for him to stop. So if you were to graph this thing, what would you put on your x-axis and what would you put on your y-axis? Yes?
Your x-axis would be how fast the car is moving, and
Okay,
the y-axis, because that's what you can change yourself. You can choose how fast you want the car to go before you attempt
Beautiful.
to stop.
Okay? Beautiful. This is what we're controlling. We're going to tell Ryan, hey, this is how fast we want you going when you cross this mark. Okay? So that's our independent variable because that's what we're going to control. The stopping distance is dependent upon that. Now, when you all do graphs, and you all do a lot of graphs in this class, make sure that, number one, you label what this is so that I know what it is. And then also what units this thing is going to be measured in. Okay? Because if all I see is a bunch of numbers down here, that has no meaning to me at all. Now, if you put velocity in meters per second, oh, okay, hey, now I know what that means. Then over here, I'm going to have my stopping distance, which is tough to write sideways, but pretend that I can. And that's going to be meters. Now, one of the things that you want to be able to ask yourself when you begin to look at graphs is that, is the graph going to start at 0, 0? So, is this graph going to start at that point? Do we know that 0, 0 is going to be one of our data points?
Yes.
Lauren?
Yeah,
Yeah, why?
because if you're not moving your stopping, it's obviously 0 meters.
Yeah, if I'm not moving, guess what? My stopping distance is a big goose egg, right? So we know that's going to be one of the points. So here's the question. What's that graph going to look like? We know it's going to start at 0, 0, but then what's it going to do?
Perhaps a constant.
Okay?
Graph.
Kind of a 70s disco move. Okay? So we got this action going, right?
Yeah.
Something like this. So it could be a linear disco move, where that would be y equals mx plus b. Or it could be a quadratic disco move, which is more advanced, and we'd have y equals kx squared. These are, without doubt, the two most common graphs you're going to see in this class. Okay? They're both a direct relationship, but this is going to be a direct linear relationship. This is going to be a direct quadratic relationship. Okay? But these are the two graphs that you will see most often in this class. Now, how could this graph justify lowering the speed limit to 20 miles per hour in the school zone? Yes? Again.
See if that it would take less time to brake, so you wouldn't endanger the person's life as much. You'd have more time. You'd have more time to react because you'd need less time to brake.
But so now you're right, but let's clarify this. You're talking about time. What are we graphing?
Distance. So you have more distance to brake in response
You
to
could-
something.
Break in less distance
I could brake in less distance.
when you're going slower.
Now, are we talking about the braking distance, or am I talking about my stopping distance?
Your stopping distance is
Stopping distance, right? So I slowed down because at a slower and slower velocity, the distance that it takes to stop, this is after I hit the brakes, okay? And so you were talking about time, okay? Time has nothing to do with this story. You're right, okay? But that isn't what we're graphing. So on this one, I know if I'm going slower when I hit the brakes, that's going to stop in a shorter distance. So this is why when you go through a school zone, they slow it down to 20, so in case Timmy goes running out into the street to chase the ball, hey, you have a sporting chance of stopping before you hit Timmy. By the way, Timmy is a generic kid that I'm going to use all the time, okay? So get used to hearing about Timmy. Like when we get into gas laws, I can explain to you all the gas laws in the world using a first grade class full of Timmys, okay? It's pressure, it's volume, kinetic energy. So you'll hear the word Timmy a lot. Sometimes Timmy needs like an untimely end, like when he goes to the zoo and he gets too close to the lion cage, but we'll save that for later. Okay, so the faster you go, the stopping distance becomes larger. And that matches what we perceive as the reality of our existence with cars. Now, but what if, and it's not, but what if we graph the data and it was this red line? What would that mean?
The faster you're going, the less distance you need to stop.
Exactly. If the red line was the reality of how we drove, what would they make you do in a school zone?
Speed up.
Yeah. Oh, speed zone. Oh, school zone ahead. I got to get up to like 100 miles an hour so that I can stop in time. Now, the other thing is that the slower you go, the greater the distance, stopping distance will be.
Yeah.
So imagine if you've all seen the carnage out here that happens with car wrecks, like out here on 45th and the parking lot. Under these lines, imagine what would happen if the reality was this line. It would be chaos, okay? But it would be kind of cool, like if you go to like parking your mom and dad's garage, and you have to like stop in a pretty short distance, like, oh, mom, dad, I gotta get up to 80 so I can stop inside the garage, okay? Which would be cool, don't get me wrong. But this doesn't match the reality of what happens when we're driving. The faster we go, the greater the distance is gonna be. So, you got your independent, you got your dependent variable. This is what you're gonna control. This is what changes as a result of it. So what we're going to look at is a spring. Now, springs are kind of cool if you think about them on like what's happening on an atomic level. So most springs are made up of iron. And you've got your nucleus, right, going back to chemistry, where you've got your protons and your neutrons. And you've got this massive electron cloud that's around it. So like on an atomic level, if you model an atom as being like a football stadium, so the nucleus would be like a baseball on the 50-yard line, and the rest of the stadium would be filled up with the electrons. Okay, that's kind of about the scale. So what that means is that everything around you is like mostly empty space. So this table is mostly empty space. And you're going, no, it's not. Look, it's a table. Seriously, it's not empty space. On an atomic level, it is. It appears solid to us because of the interactions of the electrons. So the other cool thing about this, and this is going to get a little bit cosmic, okay, but stay with me here, is that if you look at what happened in the evolution of the periodic table and how different elements were formed. So if you look at us being primarily composed of carbon, oxygen, and nitrogen, well, the first generation of stars that formed after the Big Bang were only formed, number one, because of gravity. So gravity is like the sculptor of the universe. So you had gravity pulling in, and the only elements that existed at that point was hydrogen. If you really wanted an easy quiz, go early Big Bang, and we're going to have the quiz on the periodic table. Okay, hydrogen. Okay, boom, that's it. There you go. See, all you have to do. And then hydrogen began to fuse together, and that produced helium. Okay, that's what's happening in our sun. Right now, our sun, billions of tons every second are being converted from hydrogen into helium. And out of that, you get a release of energy, which is how we get this big, ball of light up in the sky. But then, that first generations of stars, then they had to collapse. And then that's where you began to get the heavier elements of carbon, nitrogen, oxygen. And then you'd get like collapse of like a supernova, and then that's when you would get like even the heavier elements of iron and things like that. So, we exist, and this is where this is a little bit cosmic, and it sounds like something out of the 60s, and we should all be wearing tie-dye, but in reality, the situation is that we are all made of stardust, okay? All of the complex atoms that exist in our body were formed in the death of stars. And then those got ejected out, swirled around, boom, coalesced, hey, we're sitting here in room G20 at Mapes High School because of the deaths of a whole bunch of stars, and then that all stuff got recycled, and here we are. So, if you look at what happens on this spring, so one of the things you'll hear me say again and again and again is that Mother Nature is a lazy prima donna, okay? So in my mind, Mother Nature wears like this big flowing tie-dye dress, silver hair, sits around on the weekends and smokes hookah, okay? Drinks green tea. Herbal tea, so she's this really chilled out old gal. So when you look at what that implies is that Mother Nature is only going to do what is easiest for Mother Nature to do. Okay, she's not going to do any extra work. So when I look at this spring sitting here, I know that that's at the lowest possible energy state because Mother Nature is lazy. So if I pull this down and I let go of it, it returns to that point. It returns to that point because that's the lowest energy state. If I pulled it down and that put it into a lower energy state, it would stay there when I let go of it. But it returns back because that's the easiest energy state for Mother Nature to exist in. It's kind of like this. Let's say, in case you haven't noticed, organization really isn't my strong suit. But let's say, God forbid, that I lose something up here on my desk. Now, there's two places I could look. I could look here, sitting on top of the hydrant, okay, right here, like this might randomly show up here. or it's going to end up in the bottom of the shallow sink up there. Where am I going to look first?
Shallow sink.
The shallow sink, because Mother Nature is lazy. That's the lowest possible energy state for that thing to exist. It's not going to end up here. If it is, I'm going to think, oh, hey, go ahead and set it up here, okay? Because that's a higher energy state than that. So if you look at what happens on atomic level, when you stretch that out, you have these particles, number one, they're very, very tightly bound together. If they weren't tightly bound together, it would be a liquid or a gas, okay? Hydrogen, nitrogen, oxygen, okay? Big elements, but especially nitrogen and oxygen, which make up most of our atmosphere, exist as gases because they run into each other and they don't stick. Iron, when they run into each other, stick together. So it's kind of cool if you think about what happens to this. When I stretch this down, something has to stretch on an atomic level. Okay? These atoms are getting further and further and further apart. Okay? Are you stretching the electron cloud? Are you physically pulling apart? What's happening? Then, when I let go of it, whatever I distort then has a memory. And it goes back to that point. That's the whole point of a spring. Now, it would be cool if your car had that same material. So like, let's say you're in a fender bender, and somebody hits your car, and the material in your car, right, is made up of like springs, and it would just bounce back to its original shape. It's like, oh, hey, if you want to make a lot of money to build cars that are in a wreck, they just spring back. Okay? We haven't gotten to that point yet. It would be cool if we did. But springs, in effect, on an atomic level, have a memory. They remember where they should go. So when I pull that down and let go of it, they go, oh, we need to go back to where we were, because that's the lowest energy state. Okay? Everybody cool with this? All right. So we're going to look at two things. We're going to look at force and we're going to look at elongation. Okay? Those are the two things. So there's a couple of ways that I could generate force on the spring. One option is that I just grab a hold of it and I pull it down. Okay? Now, as human beings, we've done some cool things. Sent people to the moon, you know, air travel, TikTok videos, really not real high up on there with that, but we've done some cool things. But we're not very good at measuring force in terms of like a scientific process. So I could come in here and say, well, if I apply a little bit of force, I get a little bit of elongation. Now, let me clarify what I'm talking about with elongation. When I'm talking about elongation, I'm not talking about the length of the spring. I'm talking about how far it moves from that equilibrium point. Okay? So if I come in here and say, hey, I'm just going to apply a little bit of force, that thing might stretch like 3 centimeters. So this could be a data point. A little bit of force and 3 centimeters. Okay? All right. So, well, come on, Bergkamp, you can do better than that. Okay. So I'm going to apply more force, and then I'm going to get an elongation of like 6 centimeters. Okay. All right, cool. It's like, oh, come on, Bergkamp, you got more in you than that. You know, you're not that old. Come on. And so, okay, all right. I'm going to apply a lot of force. Okay? And then I'm going to get maybe like 12 centimeters of elongation. But it's tough to graph a little, a lot, and some force. So like, okay, let's find a way to quantify this. So what we're going to do is we're going to let gravity apply that amount of force. So what you're going to do is you're going to pick some weights and you're going to hang them down and you're going to see how much force it's going to generate. So let me give you a hint. We've got these cute little 10-gram masses. Okay, don't pick these. Okay, because if you hook that up, technically it's going to stretch it, but maybe like the width of like, you know, a couple of human hairs. So this is the category kind of go big or go home. So let's say you go, okay, well, Bergkamp, let's start with, I don't know, maybe a 200-gram mass. Okay, that has a nice heft to it. So I'm going to hook up a 200-gram mass and then I'm going to measure how far that thing is going to stretch. So, to calculate that amount of force, what you're going to do, if you look on your purple equation sheets, or your white ones. So, you've got on here an indirect way, and I want to make sure everybody's clear with how you're going to use these equation sheets. Over here, you have A equals force net over M. Okay? So this is technically what's on your equation sheet. Usually, the form that we express this in is it's the same thing, because if you multiply both sides by mass, you have force equals mass times acceleration. Okay, so that's the one that you actually end up using in this particular lab. Now, when I talk about weight, okay, listen to me very carefully. You'll hear me say this again and again and again. In a physics setting, when I'm talking about how much something weighs, I'm talking about the gravitational pull between that object and this earth, and this big rock that we're on, okay? So in a physics classroom, weight is going to be measured in newtons. So weight and gravitational pull mean the same thing, okay? Weight is not pounds. That's what you all are used to thinking of it because of the British system. Okay, how much do you weigh? I don't know, 150 pounds. In a physics classroom, when you're talking about the weight of an object, you're talking about the gravitational force between that object and this big rock that we're on, okay? So, a lot of times what you see this written is if you're talking about weight, it's going to be Fg equaling mg, okay? Now, all that is a fancy way of saying F equals ma. So, on Earth, unless you're specifically told differently, the acceleration due to gravity is 9.80 meters per second squared. Okay? That's a number you will remember well after you get out of this class. It's like, oh, what's the acceleration due to gravity? 9.8. Okay, everybody remembers that, 9.8. So what that means is if I drop something, okay, that's the rate at which it speeds up. So for every second that it falls, it speeds up 9.8 meters per second. So it goes from 0 to 9.8 to 19.6 to 29.4. That's the rate at which the velocity changes. Okay? If I throw it up in the air, that's the rate that it slows down, and then that's the rate that it speeds back up. Okay? So that's the acceleration due to gravity. This isn't gravity, whatever you do, and I'll flip out and you'll see why later on. Do not tell me, oh, gravity is 9.8. No. Gravity is not 9.8. It causes an acceleration of 9.8 meters per second squared, don't get me wrong. But gravity is not 9.8. Let's get that straight right now. Okay. So if I want to find the gravitational pull between this 200-gram mass and the Earth, what I'm going to do is I'm going to take 200 grams. Now, I'm not doing this to insult anyone's intelligence, but you all have been out of practice for a while. So, on the back of the yellow sheet, okay, you got to know how to use this. Here are all the prefixes that you're going to use and what they mean. So, in this case, I want to convert grams into kilograms. So if you come up here, you see, oh, kilo, right? That's 10 to the third. So that means if I have 1,000 grams in 1 kilogram, okay? So if you're not sure what your prefixes are, the ones we're going to use most often are kilograms, centimeters, and like millimeters or milligrams. Those are going to be the 3 that we're going to use most often. And even out of that, without doubt, the 2 we will use most is kilo and centi. So centi is like a century, it's 100. Those are the 2 that we will use most often in this class. We won't get into like tera and giga and pico and all that until either we get into the units on electricity or we'll use the really small numbers once we get into like nuclear reactions and things like that. But for now, without doubt, the 2 that we will use most often are kilo and centi. So we divide by 1,000, check my math, we get 0.2 kilograms. So if I want to know what that gravitational force is between this 200 gram mass and the strange rock that we're on, I'm going to go, oh, okay, F equals ma. So I'm going to try and find the weight of this. So that's going to be 0.2 kilograms times 9.8 meters per second squared. And I'm going to get 1.96. It's like the bat phone. I've never heard the phone ring. Yellow. Yes. Yes. Okay, all right. All right. I say that. Brady, calculator from, you don't have to go right now, okay, but she has, that was the library, called in the bat phone. Must have been important. They've got your calculator, okay, which might be code for an atomic bomb, I'm not sure. Because they call it on the bat phone. It's like, seriously, I have never heard that phone ring in my entire life. We just got it this year because they took off the old ones. It was like, whoa. Okay, so go get the calculator. Okay. All right, so we're going to take 0.2 times 9.8. We're going to get 1.96 newtons. Okay, easy peasy, life is good. Got it? So on the back of the lab, okay, so you're going to pick whatever masses that you want. Now, I'd have some variation on the theme, okay? Don't start with anything less than like 200 grams, okay? Because that's going to be really tough to measure. So what I would do, if I were you all, then I'd come in here and go, okay, here's this data table, and I've got the mass, and then FG and elongation. So I'd put 0.2 kilograms, and then on the front, okay, I tell you, right up here, big bold letters, Fg equals mass times 9.8 meters per second squared. So I'm going to take 0.2 times 9.8. I'm going to get 1.96 newtons. And then over here, I'm going to have the elongation. Okay? So in that case, keep in mind, I want the elongation. I don't want the overall length. Okay? I want the elongation. So the easiest thing to do is actually measure this, like in its, in its normal state, and then hook that up, and maybe this is like 10 centimeters, and then you'd hook that up and measure it again, and maybe it goes to like 12 centimeters, and then your elongation would be 2 centimeters. Okay? Now, so when you do this, don't go like 200 grams, and then go, oh, I'm going to use this one, and now I'm going to make it 210 grams. No, don't. Okay? I'd go maybe like 200, 400.